Let's talk about the ratio test, and then later we'll talk about the root test. So on the screen here, you can see a summary of the ratio test. This works for any type of series. You would compute the limit of the absolute value of the ratio between consecutive terms. So we have an plus 1 over an, or if it's k's, you have a k plus 1 over a k, etc. All right, so you compute this limit and you make a decision based on how it comes out. So if you get a number that's less than 1, including 0, then the series that you started with is absolutely convergent. If the series started with all positive terms anyways, it's just regular convergence. But if there were any positive negative terms, you have automatic straight path to absolute convergence. If this comes out to a number greater than 1, including the infinity case, then you would conclude your series is divergent. And the only time the test is inconclusive is if this limit comes out to exactly 1. The test being inconclusive means you still have not answered the question converge or diverge. You have to try another test to try to figure it out. Okay, so I'm going to do 2 examples with the ratio test, and then we'll come back and talk about the differences between that and the root test. So my first example here is the sum from n equals 1 to infinity of -2 to the n and over n squared. Okay, so we also might realize that this is an alternating series, so we could do the alternating series test, but for the sake of this example, we'll do the ratio test. So I want to compute the limit as n approaches infinity, the absolute value of an plus 1 over an. So that is the limit as n approaches infinity, big absolute value. So I'll have -2 to the n plus 1 over n plus 1 squared. That's my numerator. The denominator is just the regular formula as is. So that's -2 to the n over n squared. And of course, looking at this giant fraction sandwich is unpleasant. So we're going to immediately switch it so that it's the top times the reciprocal of this denominator. And then we'll have an easier time figuring out what we're looking at. Okay, so I have just the n plus 1 term. And I have times this term upside down, so that's n squared over -2. Okay, so I have some cancellation here. We have different powers of -2 that can cancel. So all n of these cancel with n of those. So there's one -2 left over up top. The n squared and the n plus 1 squared don't directly cancel each other at all, but we can combine them into n over n plus 1 squared if we want to think of it that way, or just leave them as they are, which is what I'm going to do. So we have the limit n approaches infinity. I'm going to keep those absolute values here for now. So I have -2 n squared, and then on the bottom we have n plus 1. So this limit without the absolute values would come out to -2, because I have n plus 1 squared on the bottom is n squared plus 2n plus 1. So I have -2n squared over n squared. With the absolute value, it just becomes a +2. This limit is +2. Okay, and then I'll consult my ratio test. I got a number that is larger than 1. So I'll conclude that this series is divergent. And that's it. Okay, let's do a second example here. Converge or diverge. Here's another series. This one has a factorial in it. Anytime you see a factorial in the formula for your series, if you have the option, you should go straight to the ratio test because it works well with the ratio test. Okay, so we'll jump right in. We want the limit as n approaches infinity, absolute value of the n plus 1 term. Over the n term. This looks really hideous, just like before. So I'm going to write this as times the reciprocal of this denominator to get the following. I also want to point out before we get too far that when I plug n plus 1 into this 2n factorial, It has to hit the times 2 first. So we get 2 parentheses n plus 1. So really this is 2n plus 2 factorial. In this step, I'm also going to drop the absolute values. I don't have to drop it so soon. I could take it to the end the way that I did here and then worry about it. But if we take a second to think about it, all numbers involved here have to be positive. So the absolute value isn't really doing anything. So I'm going to drop it and we get 3n plus 1 over the 2n plus 2 factorial that we discussed a minute ago. And then I have times the reciprocal of that denominator. All right, now I have some clear cancellation and some less clear cancellation. Certainly the powers of 3 are going to interact with each other. So this 3 to the n cancels with these, and I get 1 3 left on top. Now for the factorials, I want to kind of spell out what these factorials mean so that I'm careful about this cancellation. 2n factorial is 2n, 2n minus 1, all the way down to times 3, 2, 1. 2n plus 2 factorial starts at 2n plus 2. 1 less than that is 2n plus 1. 1 less than that. 1 less than that, all the way down to times 3, 2, 1. So if you notice, 2n all the way down to 1 is right here. So all this cancels with all of this. And we have these 2 terms left that didn't perfectly match up. So that's what's left in my limit along with the 3 in the numerator. So I have the limit as n approaches infinity. I have the 3 up top, and that's the only thing there because the entire 2n factorial just cancel. And then down here I have these 2 guys. 2n plus 2, 2n plus 1. Okay, so as n approaches infinity, I have 3 over terms getting larger and larger without bounds. So this limit is 0. And if we consult the ratio test, we got a number less than 1, which was 0. So we can conclude that our series is convergent. Or if it's of interest, we could say absolutely convergent. Here I'll just say convergent since it's all positive terms. All right, so my very last example, you can see calls for the root test. And we can tell the root test is more appropriate than the ratio test here because of this 2n power outside of my formula for the terms. So I'm going to come back up to the ratio test and turn it into the root test. So if it's the root test instead, all we're going to change is this expression right here. So you still compute the limit and you still have these same 3 conclusions, but you're computing the limit of the nth root of the absolute value of a. So we have a 1 over n exponent, that's what the nth root is. We do still have the absolute values, but we don't have to worry about the n plus 1 term. This is just one singular formula right here. And then we get all the same conclusions. If you get a limit less than 1, you're convergent, greater than divergent, and if you get exactly 1, the test is inconclusive, you've got to try something else. So let's come back down to that example. And we'll put this formula into the root test. So I have the limit as n approaches infinity, the nth root, the absolute value of this formula. In this particular case, all these terms are positive. So in my very next step, I'm going to completely ignore those absolute values because they didn't actually do anything. This nth root is the same as the 1 over n power. So we have 2n as a power and then raised to the 1 over n power. The n's cancel. So I have this and this 1n cancel out. So 2n over n is just 2. Okay, so what is left is the 2n over 4n plus 5. Now it's just raised to the plane 2 power. There's a couple different ways to tackle this limit. What I'm gonna do is see it as the top squared over the bottom squared. You could also say, well, without the 2, this goes to 1/2. So overall it goes to 1/2 squared, which is a quarter. What I'll do is go one more step and square the top and the bottom. So distribute that square to the top and bottom. This denominator, I don't need to FOIL it all out. I know that the first term, if I FOILed it out, would be 16n squared. And then I can use my leading terms business to say 4/16 is 1/4. So we could see it as a rational, or again, we could have gotten that 1/4 by seeing a half come out right here and then square that half. Right now, the root test has the same conclusions as the ratio test. We got 1/4, which is a number less than 1, so we're going to say convergent.